Hi, my name is Peter Litsky and I'm a biology professor at the City University of Hong Kong. Today I'd like to invite you to play an imagination game with me. Let's imagine that the world is ravaged by a terrible disease, let's say leprosy, and every human and almost every animal suffers from it. But by the rules of this thought experiment, scientists cannot understand what causes the disease. We see that people slowly deteriorate, get sick and die, but for some reason we cannot identify the causative agent, the Mycobacterium lepra. So let's try to imagine what would the titles of research papers look like and what the scientific mindset become in such a strange and unfortunate situation. I believe that since we would not be able to find a single cause of leprosy, we would start believing that the individual symptoms of the disease are independent, self-driven events that cumulatively lead to illness. And we would conclude that a single root cause of leprosy simply does not exist. Next, we will build what we might call the hallmarks of leprosy. This would be a description of multiple biochemical and physiological changes like tissue remodeling, blocked autophagy, altered lipid droplet metabolism, epigenetic alterations, disrupted intracellular communications, metabolic rewiring, deregulated nutrient sensing, mitochondrial dysfunction, immune reprogramming. These effects would exist somehow without a general framework or any central organizing element, and with little or no hint that the bacterium may be involved. Then, a major advance in our understanding and treatment of leprosy would be the development of methylation clocks. By studying epigenetic alterations in patients' DNA, we would build predictive algorithms to track their progression through the disease. These clocks would work with reasonable fidelity and we would be very excited about them because even if we still could not explain what leprosy is, at least we could measure something. This clock would allow us to test interventions, potential treatments for their ability to slow leprosy, but would this approach be 100% effective? No, they are diagnostic tools. And like all diagnostic tools, the clocks would have shortcomings. Take thermometers, for example. They were a great invention for healthcare, but they do not cure infectious diseases such as influenza. Moreover, if we try to develop a cure for influenza based on the ability of compounds to control temperature, we would probably end up with very good fever-reducing drugs. But they would not target the disease itself, and they might do more harm than good. The same would be true for leprosy methylation clocks. Nevertheless, unable to cure leprosy or understand what it really is, we would recruit scientists from other fields, for example, physicists, who would try to rationalize what is happening with physical formulas and feed biochemical readouts into their theoretical framework. This would lead to the emergence of new and exciting field, leprophysics, which treats leprosy as a direct consequence of entropy. These and similar ideas, together with our helplessness in curing the disease, would lead to the view that leprosy is fundamentally incurable, and that even the phrase anti-leprosy is an oxymoron. This failure would then shift our attitude. Instead of trying to cure leprosy, we would say that we should simply improve the quality of life for these who suffer from it. This would produce the health-pressy approach in medicine, aiming to help people live healthier lives as long as possible, but only before they die of disease. Still, some brave people would try to borrow ideas from other fields to mitigate the problem. For example, partial reprogramming of cells with Yamanaka factors might become one of the promising approaches. But let's ask ourselves, would this really work? Is it a truly rational idea? The logic behind partial reprogramming is that the patient was healthy at some point And then something went wrong. With reprogramming, we try to turn back time and return this person's cells to a healthier state. However, in the case of leprosy, things are more complicated. We cannot truly reverse time. We can only reverse cellular states. The reprogrammed cells would be reinfected by the bacterium. The method would not produce health outcomes. But without knowing about the bacterium, we would not be anyhow able to foresee that. Another similar approach would be replacement therapy. We might try to replace damaged tissues, for example, transplant new fingers or new eyes to these poor patients. Again, this would seem like a kind of a time machine, but would it work? No, the bacterium would infect the newly transplanted organs as well, and the benefit to the patient overall health would be minor. So, both reprogramming and replacement are attempts to create a panacea, an intervention that could in principle work for almost any disease. Any disease that affect particular organs or cells, and nearly all diseases do so, could potentially be targeted by reprogramming and replacement. However, if we do not understand the nature of disease, these ideas may seem to be much more promising than they really are. If we carefully consider reprogramming and replacement, we can see that for infections, autoimmune or genetic disorders, they may not be the best approach because the newly reprogrammed or transplanted tissues will again be infected, attacked by immune system, or affected by the same genetic defect unless gene editing is also applied. But if we do not know the etiology of these diseases, reprogramming the replacement strategies may still appear very attractive as they seemingly revert time. Coming back to leprosy, one of the ambitious directions would be also called leprosy escape velocity, the idea of extending the lifespan of existing patients even modestly so that they can survive long enough to see the final cure. As a plan B, we would see cryopreservation, freezing patients to postpone the problem until the cure is found and a reliable refreezing protocol is developed. Alternatively, we may think also about mind uploading as a way to preserve our personalities in a form of computer simulations. This approach aims to escape the fundamental limits of our body and make people cyborgs. So I would bet that all this would continue for a long time with little real progress until we finally discovered the goddamn bacterium. Once we found it, we would likely forget much of what we have been studied before, and sooner or later we would develop antibiotic and cure the disease. From the moment the bacterium is discovered, leprosy stops being a fundamental scientific problem and becomes an engineering problem, but not anyhow before. Yes, why do we play this silly game, you may ask? Because it's not random. It's a harsh sketch of what is happening in aging research today. We still do not understand what aging is. Is it curable? Is a disruptive discovery in aging possible? And if such a discovery could truly change the game, where might it come from? If you are curious about these questions, I wrote a book about the search for a new paradigm of aging. And on June 12th in San Francisco, I will be giving a book presentation. You are very welcome to come, discuss some ideas and much more ideas, and get a signed copy. Please don't hesitate to ask questions in the comments, and I will try to do my best to answer them. Immortality in progress. See you in San Francisco, June 12th.